So, you know, I'm an experimental physicist, and when I think about physics, about like designing detectors, detecting stuff, then, what are we measuring? How we build something that's going to detect what we need to measure? Kind of try to think along those lines. I'm always trying to, go through this process, like, you start from one point and continuously, you add like little steps until you reach, your final destination, your measurement or whatever. So we're going to try to do that here with you all with mu on G minus 2 experiment. So we'll, start little by little, and we're going to add elements, and hopefully by the end, we're going to have an experiment. Of course, that's going to be a very difficult thing because building something like the G minus 2 experiment requires a lot of, knowledge. But hopefully, I'll assist you with that knowledge, and we'll have a conversation. I'll ask, a few questions to create that environment, and then move forward. But before we even start that, we need to establish a few things. So, what is particle physics? So, let's read what it says. Particle physics define the masses and interactions of fundamental particles that makes up the. So, what does it make up? What's this particle interactions are making up? Could you tell me? Let's start with a question. Okay, you have a
Model.
yes. So that's how this is going to go. Of course, you're not going to guess everything right. I mean, it's we're not here to test your knowledge. Okay, we're just trying to have a conversation. So yes, this particle physics as part of physics, it describes the masses and the interactions of all these particles from like muons to quarks and the neutrinos, and all to intermediate particles like photons, like gluons, bosons. And at the center, this like the newest representation of the particle physics as we know it. You have the famous Higgs boson at the center of it all. So what we're concentrating today here will be the muon, shown with the Greek letter mu. That's the particle we'll be interested in. So standard model, what does it look like? So apparently it looks like something you can buy from the gift shop and give it to someone you love. It is, it's this way because it's like pretty famous. It's like the most important theory in particle physics. It's quite, complicated, and this shows you this thing called Lagrangian, which defines in a mathematical form what I just said to you, like about the masses and all the interactions between those particles. But what does it really look like? Not on a cup or a mug. It really looks like this. Okay, I think when you look at the whole thing, the whole Lagrangian, it looks horrible. Okay, and it doesn't even explain gravity. Like, what kind of theory is that? But it is what we have. Okay, and this is why we need to make this prettier and nicer. And even with this, with all this stuff in there, crammed in there, it doesn't explain everything, right? So that's why we're here at Fermilab trying to find new physics, and everywhere around the world for that matter. Okay, I'm going to talk about some physics experiments. So in the U.S., we divide the particle physics into different categories. It's not the same everywhere else in the world, but in the U.S., there are like three major ones. So the first one is called the energy frontier. So here, when you think about energy frontier, you should think about like colliders. Here's a clip from Matrix 2, where like two trucks are colliding each other, right? So that's exactly what you're doing at the collider. You have particles, you try to, accelerate them and, try to make a head-on collision. And when they collide, like all this stuff, like in the clip here, just starts flying everywhere, right? So what you do then, you put your detectors and try to see what's coming out. Like, so, oh, there's like a tire. So that means the truck has a tire, okay? And that's, that kind of thinking is like what's going on with the energy frontier. I mean, the flagship facility for that is CERN. I'm sure you all know it, at Switzerland. And the two biggest experiments from CERN are the CMS and the Atlas. And at Fermilab, we have a big presence on the CMS experiment. Even though the collisions are happening halfway over the world, there are physicists here working on analyzing the data and such. So the other one is cosmic frontier. So the cosmic, you think of space, you think of dark matter, dark energy, you think of telescopes. Most of the time you're looking at the space and measuring things. So here are some experiments that Fermilab also have some connection to. The cosmic frontier isn't only just telescopes, mind you. There is a whole breadth of experiments you can do actually without looking at the space. Even at muon G-2, you could see if you can detect dark matter. So it's a whole range of different experiments. So it's pretty wild. But if you think about telescopes and looking at space and try to understand that, that's not far off. And finally, our frontier, intensity frontier. So this baffles me because when you say intensity frontier, that doesn't really ring a bell. But let's try to think about that. So when you say the intensity frontier, you're trying to think of rare processes, okay? And since they are rare, you need precision measurements to find those processes, right? And kind of that ties into the intensity because, usually you have intense beams to get a lot of particles and then try to make these precision measurements. And hence, I have the picture of a clock ticking at a certain frequency here. So we have the experiment. That's the big one that's coming up, multi-billion-dollar project. But we have also here at Fermilab, we have G-2. We're talking about that right today, and we also have mu-T, which I also work on. It's a great experiment, but it's currently being in construction. So it will be the running experiment after muon G-2. Okay, so how do you find new physics? So physics at its core is an observational science, okay? So to start, doing anything, you need to have an observation. And then you're kind of sitting there and thinking, oh, why did that happen? I have to explain that. You have that curiosity accompanying you, okay? So let's give one of the first examples. This is Newton's universal law of gravity, okay? So this is the story always been told, you have this apple that's falling, okay? So that's your observation. You're saying, oh, why does all these things just fall to the ground, right? And then you start you start answering these questions. So at first, this is about philosophers talking about philosophy, maybe the Earth is the center of the universe, so maybe that's why things are pulled through. But you're kind of doing a thinking exercise at that point. So etymologically, the physics and the philosophy, they come from the same root. So once you start using math, your philosophy actually takes form. Then you can actually write things down and show things more sensible manner. So that's then philosophy turns to physics. Okay, so then okay, so there must be a force. You know, it should maybe it's like there are two things gravitationally attached to each other, and then like they're pulling each other. Okay, so you work on this idea. So that's the theory, and then Newton's come up with I have like two objects with mass m1, m2, and the force between them, proportional to their masses and inversely proportional to the squared distance between the two mass. And then I put a like constant there, g, the gravitational constant, and that's give you the force, and that's why then we can space we can send like stuff to space, and they orbit around. So once you write that theory, then you got to do the experiment, okay? Because yes, you did come up with something, but you don't know if it's really true. You have to match your measurements to your theory. So that's the experiment. Here, like in this example, Henry Cavendish in 1798 makes this torsion pendulum experiment, and then shows, oh, okay, this works out, and then you make a discovery. Okay, I have to note that like this 1798 date is like 100 years after Newton came up with the theory. So it's 100 years you had this theory, but you didn't really know if it was real. So many steps later, okay, so the physics and everything, for that matter, science, let's call it science, it builds up on itself by layer by layer, okay? So, this one observation leads to like another experiment leads to another observation, and so on and so forth. So many steps later, what you end up with in particle physics, you end up with all these particles. You put them there, and you're like, oh man, what's in the middle? And then you guess it. Oh, there must be like this Higgs particle that binds it all together and give particles their masses. So you theorize that, right? So that's the standard model. Okay, you start writing your standard model, and you do the experiment. So now, of course, many steps later, finding things are harder. Okay, so building this collider, collecting all the data, differentiating different particles, it's really complicated. But we put millions of dollars or euros in it, and then we make it so. And you have the measurements. And to 2016, we found what the Higgs was, the Higgs mass, the theorized Higgs. Again, this was 2016, but the Higgs was postulated like 60 years ago. So again, from the theory to the measurement, we have to go through that technological advancement to make actually a discovery. So what's the muon? The muon experiment, we need to explain what muon is. So this part of the pie here has three particles: the tau, muon, and the electron. So these belong to a family called leptons. Okay, so these are like charge spin half particles, charged particles, and here are their masses. So electrons is 0.5, muon is like 100, and tau is like 1,000 MeV over C. So when you look at this thing, the muon is the middle sibling of the family. I mean, simple terms, it's just like a fatter or more like larger electron. Okay. The important thing here is that muons are useful as discovery tools. So in physics, when we look at the masses, like you look at the mass ratio of the muon to electron, and it's like 40,000 bigger, and that's kind of feeds into your like mass scale, and that leads you that you're more likely to find new physics, more likely to probe particles, different particles at like higher energies. So that's why we like muons. tau is in the same sense. Tau is bigger. It's better, but um, all these particles, like the muon and tau, they're not stable particles. Okay, they decay. So the tau's lifetime is much shorter. So here, when we say relatively long time with the muon, that's something we could use in our experiment. So it's good for making experiments around. 2.2 microseconds. So microsecond is what? How much of a second? The microseconds is billionths of a second. It's you think that's like too small, but we're going to talk about like why that's something something important to us, something that works for us. Also, what I say here, easily produced from pion decays. So we'll talk about that again later about what pion is, not what pion decay. Okay, so difficult stuff. So what is muon's magnetic moment? So another concept that we're going to use in our experiment is the magnetic moment of the muon. So we have to go through this. And this is one of the two formulas that I'm going to use in this presentation. So we don't want to get too technical in the math, but these are like simple enough. So let's see what it is. So what I wrote here is that magnetic moment is the magnetic strength of the magnetic object. So basically, that magnetic moment describes what's going to happen when you put like a magnetic object near a magnetic field. Okay, how they're going to affect each other, basically. So for particles, elementary particles, that's all about this thing called spin. So first of all, have you ever heard about spin at all? You heard about it, you don't know what it is. So last night, going through like how can I explain like spin to students? It's really hard, and it's really hard because spin is a quantum mechanical concept. Now it doesn't really have an analogy in classical mechanics. So it's really hard to imagine. So I found this funny meme, and I'm just going to read it to you. Imagine a ball that's rotating. Okay, that's spin, but except it's not a ball and it's also not rotating. Okay, so that's the key concept. Let's look at the ball, and it rotates like that. And we say that it's a spin 1/2 particle. That's how it's like that theory is formulated. And then when you turn like that, you assign this like poles. For example, arrow going like that, south to north, and then you could kind of then follow your magnetic field lines. If you reverse that, then the polarity just changes direction. So it's not a ball because, as you know probably, there's this thing called particle and wave duality. So in physics, not everything is a particle. It can be also represented as a wave. So when you think about atoms, electrons, and everything, we just kind of determine a radius where all that charge and mass is located, and they're just kind of there as like wave functions. So it's not like a ball that's spinning. And since it's not a ball, it's really hard to imagine it's spinning. But you do see the effect of this. Why? Because you have this ball called electron. Okay, so you put it through a magnetic field, and the electron with this spin goes one direction, and you switch the polarity, or you polarize the electron with you take the electron with the minus half spin, and that goes a different way. So you see the effect of this thing called spin. But it's really hard to just say, oh, this is a ball spinning. So you can't really think of that term. But like kind of everyone does, just for the sake of it. So the other two things in the formula E is the charge. So I'm not going to talk about that. The positive and negative, they attract each other. That's how we have electricity, right? M is the mass. Okay, that's also pretty straightforward. So here comes the G factor. So that's like the muon's magnetic moment, spin, and the G are the important parameters here to us for the muon G minus experiment. So this, G factor basically tells you how this muon's magnetic moment is tied to the spin, right? So if you change this G, how this spin and muon like affect each other will be different. So it's a proportionality factor between the muon's magnetic moment and the spin. So, and in theory, you calculate that, and then that tells you how that the particle is going to behave in a magnetic field. So here's a nice example that I want to show you. So this is not a particle. This is a bunch of atoms. So this is a magnetic material. Okay, you can see like they're atoms, and they all have like their own angular momentum. Let's call it spin. Yeah, they have all their own spin, and they're all like magnetically looking at like different directions. So what happened is like when you put this material under an external magnetic field, now all these formulas are going to start to work, and let's see what happens. On a loop. So your magnetic field is from the left side of the page to the right side, and as soon as they interact, all atoms like spins are parallel to the magnetic field. This is of course for a ferromagnetic material, but like all these things describes this interaction with the field and how the particles, atoms interact, with the magnetic field. Hopefully that's clear to some extent. So I, went into so much detail because we're really going to focus on this G here. Okay. So we talk about the muon anomaly. So that's when you read about muon G minus 2, it talks about this anomaly. So what's that anomaly? Because that's basically our observation. As a physicist, we look at it and we say, oh, there's an anomaly there, so I'm just going to find it. So Dirac, postulated this spins 1/2 particles in 1928. So this is basically quantum mechanics at this point. The theory was developed by then, like 100 years ago, right? So Dirac predicted this G, the G factor for electron and all spin particles, 1/2 particles, as G equals to 2. Okay, that's the original formulation. So then, what you do, you go and do experiment, and either confirm that or deny that theory, right? So that happened. 20 years later, Schwinger here, the quantum mechanics progressed. Now we have like quantum field theory where we think particles in terms of like fields. It's more advanced. And you have now when you calculate this thing with this new theory, you have like additional corrections to it, and suddenly it's not 2 anymore. Okay, it's 2 plus something. So and then that's the anomaly. Like okay, there's some problem here, and then you go measure that and see if they match up, right? So this kind of goes like this for a while. Again, many steps later, today the standard model defines the GE like this. So the anomaly is then, like in mathematical terms, is that we take this number, subtract 2 because it's supposed to be 2, divided by 2. And that's fractionally tells you how much you're off from the standard model calculation. So, and there's an anomaly because there were experiments, and they're like, hey, I mean, this G factor you're calculating in your standard model, we're experimental physicists, we're finding something different. So this just doesn't add up. So that's the anomaly. That's why they're different. The experimental value and the theory prediction aren't matching. And they're like, okay, so there must be something here. There could be like new physics here. And that's, that's your observation. And then you go, and you have your theory, you go and then do the experiment, which is what we're talking about. That's the muon G minus. Okay, so we know all these. Okay, so that's the anomaly, and that's the muon's magnetic moment modified with the anomaly. So we talked all about that. So in really general terms, what do we need to have to make an experiment? So let's hear some suggestions from you guys. So what do we need to do the experiment? What do we need? Like simple terms. We have a here.
You need muons or a source of muons.
Okay, so that's okay. It's good. We need muons. That's right. I mean, that seems like really obvious, but where do you get your muons, right? It's not a like simple answer. I mean, it's a simple question, but it has a difficult answer. Okay, we need muons. What else do we need?
Any type of neutron?
Neutron?
Yeah.
But we didn't talk about neutrons. Why do we need neutrons? Because I worked on neutrons. I mean, I would like to use them. But let's try to think about what else do we need. I mean, I emphasized a few things, right? More answers?
You need some kind of a magnet.
Yes. So we need a magnetic field, right? Is that the next thing? Yes, we need the magnetic field, right? Because when we put them, they will do stuff, right? And then we'll see the anomaly. What else do we need?
Something to detect the muons.
Yes, perfect. Yes, detectors. We need detectors. So once you have these 3 things, then the experiment is done. All right. So congrats. You guessed it right. Yeah. So like there's like 3 things there. The thing is more like infinitely complicated than this, but generally that's like how you think as a physicist. Okay. And then there's 3 things I have. If I have these, I'll make the experiment. So let's design the experiment. So there are obviously lots of other physics conclusions that I haven't mentioned yet. So one of them is that so you have your muon, you have your magnetic field. So when you put your muon into the magnetic field, so here, the B represents the magnetic field, has that arrow symbol there. That means like arrows coming out of the page. So the B field is actually towards you. And the muon going with the red arrow. That shows its momentum. So that's where it's heading, right? So when the G factor is equal to 2, the muon momentum and the spin, they're aligned, okay? So the muon in the presence of the B field starts to turn because, B field exerts this force, Lorentz force on the muon, and muon starts to turn. And as it turns, the momentum and the spin of the muon are aligned. They're locked, we say, okay? So that's what happens. But now we know there's an anomaly. G is not 2, okay? So what happens when G is not 2, when G is more than 2, is that momentum still stays the same, but the spin vector, and that spin starts to turn, okay? Because it's not 2. And of course, there's complicated math to show how that works, but that's, when you go into your physics class. But for now, we're going to accept that that spin is going to start to move away. And that we call is the precession, okay? That's the, really called the Lamer precession frequency, but basically that's the muon precession movement, which is, around an axis, your spin vector is going to try to turn, right? Exactly how it is shown in this clip here. And to make the experiment possible, we need to measure that frequency, because after some math, physics, and beam dynamics, you come to this formula. Okay, so omega A is the precession frequency, and that actually ties into the anomaly, that A mu, and the magnetic field. So let's talk about that a bit more to understand that formula. That's the second formula I'm going to show you. So when G is not equal to, we can find that precession frequency. Okay, that's what we call omega A, with just these four parameters. So the first one is E. What's that? That's the electric charge. It's the 1 coulomb. So we know that. Like, we open the book and oh, what's E? And we just put it in there. M, that's the muon mass, again, measured to quite precision. So we know that. 105 MeV, 0.105. We put it in there. So then what you need to get the anomaly is these two. You have to measure this frequency. You have to apply the B field, right? As we discussed, you have to know what your B field is, like really nicely, precisely. And then when you put the B in there and you measure the omega A, right? You put all those in there, and then you can get the anomaly. And then you have your measurement. Okay, step one. We're going to go step by step. We said we need muons, so we'll start there. We'll get our muons. Okay, where can I buy muons? So if you're wherever you work, as a physicist, as an engineer, anything. Okay, you have a project. The first thing you have to ask yourself is, can I get that off the shelf? Okay, you don't want to design something for something that's available already. Okay, for muons, you say, oh, okay, the Fermilab's making muons. We have the accelerator complex. They're the sellers of the muons. So we come here and we build the experiment here. Okay, so here's the campus. We are here. Okay, that next to this building, right? So it goes underground a little bit. That's the Wilson Hall. And this is the booster tower. This is the old tower line. There's it looks so peaceful here, but all the accelerator complex, all these tunnels and magnets, they're all underground, just filled with mazes. Crazy. So if you take this door out there and just walk a little bit, maybe 5 minutes. This is where muon G minus 2 is. This is where the ring is. Hopefully in the future, when we don't have all these trouble getting you on site, you'll come and see the experiment, at least the magnet for yourself. Since the experiment is almost done now, hopefully it'll be open for tours. Next is there's also that MUT experiment that I mentioned, which is a really great experiment, but not a topic of today. So we came to Fermilab to get these muons. Let's see how Fermilab accelerator complex creates the muons. So here's a general view. The beam starts here. So there's this source here, source of protons, and there's this thing called LINAC. So the LINAC looks like this. There's a bunch of tubes attached one after other. So this is LINAC, means a linear accelerator. So you have your protons, and then you accelerate them in a straight section. It goes up to 400 MeV. So that's the first start. That's not good enough. More. We have booster. So this is circular, as you can see. So this booster basically boosts 400 MeV protons to 8 GeV. So that's like 20 times the energy. So just they go around the circle. That's called a synchrotron. Just they go like that until they're like really fast, right? So once they're 8 GeV, then you have this thing called recycler ring. So what is the proton bunch is split into 4 bunches using RF magnet. So the thing is, like all experiments have like different beam requirements. I mean, you have this 8 GeV protons or whatever, but you know, some need like continuous beam, some need like separated beam. So you know, you want like a beam to hit your target and then wait a little bit and hit it again. Okay, so there's like different configurations. So this ring allows you to form that, you know, specific needs basically. So it just splits the beam, so it has this like particular structure, good for the experiment. So there's like 4 split bunches there. Now they go around, and then they come here. This green rectangle here is the target, the pion production target. So it hits the target. It hits the target. When it hits, the protons hit the target. These composite particles called pions are produced. As with all other, most of the other particles, it's not a stable particle, so it will decay, and we will talk about decay in a bit. Here's what it looks like. But when pion decays, you get muons. So that's, you know, how Fermilab creates these muons. Now, you know, it hits, and this is like a collision again from before, like with 2 trucks hitting, but instead a truck hitting a concrete wall. That's basically what it is. Okay, not 2 trucks hitting, it's just a truck hitting the wall. So now we have the muons. We're almost there, right? So we like push them here to this delivery ring. We're on that slide, all right? So the delivery ring kind of circles them around, give them some time so that they're ready for the experiment. What it actually does, like when you hit that target, you have all this spallation, right? All these other particles, the protons, the pions. But you know, what you end in the end, what you want is just the muons. So you kind of go through this delivery ring and make sure like the other particles are not in the beam. So like they kind of die out, right? There's you do that. After a few turns, you're mostly left with muons, a pure muon beam. Since you know we're doing precision physics here, we just want to get all the muons and get our hands on. And then after that, it comes to our experiment, and then we can start the experiment. So that's, you know, basically as we engineer this thing. This is on Fermilab. We came here like give us muons, and this is what they did. Okay, we need to store muons. By the way, when are we? Is it we're close to the break time, or how much I should go? Okay, I can keep going a little bit more, and then yeah, you can tell me when to stop. Okay, so the nature of this experiment is, you know, we're going to measure these things, and we're not a collider experiment. We're not just like hitting them and like looking at what's coming out. What we're doing here, you know, we put them in the magnetic ring, and we're going to measure them. So if you're in accelerator terms, that's storing the particles. Okay. So what we're talking about here is storing the muons. So once they enter our ring, the G minus the ring, they need to stay there for a while as we do the experiment. So to understand that, we have to talk about muon decay. So I keep, you know, talking about unstable particles, which means, you know, all particles, I mean, most particles, like they don't have like a stable like energy structure, and they decay into more stable particles. So in the case of muon, that's the muon decay. we're using positively charged muons that decays to an electron, positrons, the positively charged, and neutrinos, which we don't really care in this experiment. Well, we do when we look at dark matter, but for the G minus 2, we don't. So here is how it looks like. So this is muon G minus 2 our experiment's data right there. When you plot, a number of muons stored in the ring versus time, and you fit it, you have this thing coming down. So that's called the lifetime of the muon. Okay. So the muon is decaying with some fundamental decay constant. It's a fundamental property particle, and that's what I told you earlier in the earlier slide as 2 microseconds. So that's, however, only the lifetime in the muon frame. Okay. So when we talk about physics, always talk about reference frames, and you gotta tell which reference frame you're observing the particle. Okay. In the muon's time frame, as you are the muon and going through the ring, you have 2.2 microseconds. But as it turns out, in the lab frame, in the laboratory frame, this turns into 64 microseconds, and that's exactly what we see with the G minus 2 data. So this is due to. So what is this due to? Just let me know. Sure, some of you know. Why is this 2 microseconds suddenly turn to 64 microseconds? What's the theory behind it? Time dilation. Yeah, what's that? Which theory is that? Yes. So this is relativity. Okay, the Einstein there smiling. Yeah, it is. This is when physics starts to get interesting. This is when cosmic muons comes to Earth, they're able to make it to the ground with time dilation and so forth and so on. So this is relativity, and so now we need to design something, right? So we need to store these things. So you could do all sorts of stuff. So you could do that linear tubes, right? You could do a circular thing. You could do maybe a spiral thing. So there are a bunch of geometries actually you can choose. So, but we can eliminate some of them using this relativity. Okay, you calculate the distance traveled by the muon, and then it's just. So when we say relativity, by the way, that means the particles are moving at light speeds, okay, close to c, or comparable to c, and that's when this thing happens. It doesn't happen in your regular life when you drive for 80 miles per hour. You have to go faster than that. You have to be closer to c. Since things are relativistic, and you put the relativistic equation in there, and when you calculate this distance, at 64 microseconds, this thing is actually traveling 20 kilometers. Okay, and we want to keep them around for not just one lifetime, maybe 10 lifetimes. Okay, we have to keep them around and do this measurement. So this is by design. It kind of eliminates your linear storage, in a straight section storage design. This is not specific to muon G minus 2, but one thing maybe you should take away with is that that's why everything is circular most of the time. So you have this super particles going at super speed. You have to circulate them, otherwise you're going to run out of space. You have to put up with billions of dollars of digging the ground just to make a straight section. So that's why that necessitates that all these circular designs you see around particle physics. So yes, that's what I said. So we're talking about a circle, and it's it doesn't take too much space, so we can accommodate a place for that easily. what else is needed? So here are the muons are coming in. So we have this maybe rectangular tube that we put them into, okay, and they're kind of like that. So what we need so that they follow this circular path, we need radial focusing, right? If you don't have radial focusing, like they're not going to turn. They're just going to go straight and out of the circle. And we need the vertical focusing as well. So I mean, this we need this because we need this. Again, it stays here. Yeah, so we can store them longer, right? So see, like when you do the focusing, the effect is like they're more compressed and they're like more at the center. You want to do this because when your beam is like wider, and the muons, they're not always going on in straight tracks. They're always like oscillating. They're going to hit stuff, okay, hit stuff around inside your storage area. So to get the most muons for the longest time, you always need like a smaller beam. Ideally, you need like a pencil beam. It's like really focused. But obviously, it's really hard to get that. That's why, like with all these like magnets and stuff, what we're doing is to make them focus in the storage ring. So they're like nice and tight in the middle, and they're not like hitting anything else. And we're keeping those muons. We're storing them. We need every one of them to make the discovery. We need as many muons as we can get our hands. So that's all done via magnets. Again, the designer question, where can I get a magnet like this? Can I buy this thing off the shelf? Can I? Actually, I can. Actually, I can because the experiment was done before at Brookhaven National Laboratory 20 years ago. And we're like, I'm not going to build a magnet. I'm just going to use that magnet. And think how crazy that is. So this like 50-ton magnet traveled across 600 miles. So Brookhaven National Laboratory, isn't it? Brookhaven, in Long Island, New York. So here's the path they took. Start from here, go through the Atlantic, comes through. Look at it, it's on a ship. Can you believe that? Can you imagine that the magnet in a ship? That's hilarious. Comes like that, goes next to the Bahamas. Maybe they stop there for like 2 drinks. Who knows? Comes here to the Mexican Gulf, and then it's on the road like a truck going at a really slow speed. Like it's amazing. Like they do that. We do that instead of building another magnet, because it turns out making a magnet is like pretty damn hard and expensive. So that's we opt out. Okay, we get our magnet from the Brookhaven. Question? So this is okay. Good question. Why did they go around instead of like going straight? So the answer is always it was for some reason cheaper. I'm not really sure why they took this route, but one thing. Okay, another question. Oh, okay. Yeah. Yeah. So I mean, the whole thing was like, as you can see, the whole thing was lifted and delivered as is. And that's a great answer about like why didn't take that route. I mean, it's all, you could do that. You could do that preparation, but it's going to cost again millions of dollars. It's going to cost due to downtime, the government, another like millions of dollars because the roads will be closed and whatever. And that was the best they can come up with. And actually, few like in the past for this lecture, people ask, why didn't you fly it? That's also another option, right? But it's like super heavy, and also like when you drop this thing, it's over for the magnets and probably for people. Like you can drop this thing onto people's houses, right? And it's going to destroy their house. So this elaborate plan they come up with, and they went all the way. So that's pretty incredible. And it was a big day when it came here. I think it was 2000 earlier, around that time. That's when I kind of joined the experiment. Yeah, I think so. So it's a good time, looking at this picture, starting here. All right, 15 minutes break. Okay, you can hear me. All right, that was a nice break. I got to know you a bit more, because I really appreciate. Okay, so we're at the magnet stage. So here's how it looks like. This blue thing. It has a 1.4 Tesla magnetic field. So, and we're going to talk about like magnets and how they work in a bit. So that 1.4 Tesla figure. So that's the numbers doesn't mean anything when you can't reference them to something that you know. That this is if you consider Earth's magnetic field, that's 30,000 times bigger than Earth's magnetic field. It's a really weak magnetic field. For like a bar magnet that you can go out and I suppose buy, it's like 150 times bigger than that. There are stronger magnets, like for example 10 Tesla magnets, like we're going to use in like MUT, but it is a strong magnet. So one of you asked like what happens if there is a magnetic object in the ring. First of all, that cannot happen because we don't allow it. But if it were, they're pulled right into the magnet, and it's really dangerous. Okay. In fact, we put some protection over the whole thing currently. That's why it has like the first pictures, this white sheet hanging over, so that people go through here. They don't drop their keychains on the magnet. So yeah, it is an amazingly strong magnet, and like if you put something in there, put a steel brick in there, just going to break the damn thing. Okay. And wish what you could do. You got like a steel. Anyway, I'm not going to tell you that. Maybe later. Hidden. Okay. So this is the magnet. So of course, I'm telling you this. This is a superconducting solenoid. So you're going to ask me what's superconducting and what is solenoid. We don't know both of those things. So this is pretty simple. I mean, all like magnets work like this. You have like a wire, conductive wire, and like around something, you try to you wind that wire. You make a coil, just so, and then you put battery on each end. Like there's a positive polarity, negative, and then you run current so that yellow things represents the current. So when those currents move, they create a magnetic field due to these poles. To create a magnetic field, you always need like a dipole. Okay, you have like the positive and the negative. Which you cannot do like a electric charge where you put the charge in there and then there's the electric. You need this like current going through the wire. So that's a solenoid, that coil structure. And I get this from this Sigma physics page. It's really nice if you want to learn more about like this simple. And you determine this. Maybe you already know this, or maybe you've seen somewhere. You use this right-hand method. So you kind of grab the direction where the current is going, where the particles, the electrons are traveling, and then your thumb then shows you the direction of the magnetic field. So in this case, it's the other four fingers are direction of the. That's basically a solenoid. You get a wire, you make a coil. That's a solenoid. A superconducting solenoid is a special solenoid that has zero resistance. Okay, that means for low voltage you could pass through much more like greater currents. Okay? You can conduct larger currents. Why is that good? Because if you have more current in the wire, then you can get stronger magnetic fields. So for this experiment, like for these like really strong magnets, like most of the time, that's a superconducting solenoid or superconducting magnet. Back to here. So this cross section of the magnet here. Here's our storage area. Okay, so the red thing in the middle is the muon coming towards us. Again, this notation, this outer coil going like that, and there's also the inner coil like coming out of the page. And this blue line shows the magnetic field that our magnet is creating. So here in the storage region, it's looking up, and this this magnetic field here exerts a force on this muon radially inwards. If you look at it in this picture, like so. So now with the magnet we establish radial focusing, so it starts rotating, right? And whenever you want to rotate some object in particle physics, you need to use magnets to rotate like charged particles. So, but that's not really the whole story, okay? So what actually happens is, so now we're going to talk about the parts of the experiment, and we're going to resolve them as we go. So the muon's coming this way, okay? So the magnet has a magnetic field both in the inside and the outside. So what happens is like they're getting deflected as they try to enter the storage region. Okay. So how do we correct? Like how can we correct for this like deflection? So we want this muon to go straight. What can we do? How can we negate that outside magnetic field? Any suggestions? More magnets, yeah. In fact, is this why? Another magnet. Okay, yeah. So I mean, inflector magnets cancels deflection. Actually, the answer was written here all along. So you're working with magnetic fields. So then, like when you want to manipulate the magnetic fields, obviously you're going to use other magnets. So it's like a bunch of magnets that you place around until you get what you want. And there's like this little inflector magnet there at the entrance of the ring, so that muon, when it comes, it goes straight into without deflecting and into our storage area. So if that's the magnet, the storage area is this rectangular tube going like inside it. Okay, so we look at it. This is the injection orbit with the inflector. So when we look at this thing, it's not centered, right? This purple orbit is not centered. So if this happens, if it run it like this, all these muons I showed you, like they're going to hit everywhere, and they're not going to get stored. So we really need them at the center. So our radial focusing isn't finished yet. This is the best you can do. So we need to solve this problem with what? With another magnet, right? That's called the kickers. So we're literally, like as they go through this purple orbit, there are 3 magnetic kickers. They apply a really strong field in a like really short time. They basically kick the muons into the right orbit. That's exactly what's happening. They're not really kicking. They're changing the magnetic field, so they experience the kick. So it's but Those three things as you go through. So, okay, let me show you. So those are the kickers in the storage area. So they're here, 1, 2, 3. So as it goes through, it kicks the muon into the right orbit. So from the purple, you go to the red one. The red one is now centered. And we need them to be centered, not just for store them, but also for our calculations. Go into the details of that. And they're located here. So we actually call them bazookas. They're so strong. So there are 3 bazookas, just like boom, and they're in the right orbit. You gotta time it right, just right. So that handles the radial part. So now I'm going to talk about the vertical, because I said we want them as small as possible. We need the vertical focusing as well. So to do that, we have this thing called electrostatic quadrupoles. So here's a picture of it. These are basically like 4 plates. We positively charge these 2, negatively charge the other 2. It creates these electric field lines. So if your muon is coming right outside, it's going to exert this force on it, forcing it into the center. So if you're out there, you're going to be drifted to the center. So that's what the quadrupoles are doing, and that's basically if you're out there, if you're up here, it's going to push you down. If you're down there, it's going to push you up, so that you're at the center. Ideally, you want this thing all the way through, so that you're always super focused. But you really can't get that. There's other stuff in there. So quadrupoles are only at 4 locations. They cover 43% of the ring, but that's enough for to get our measurement. Okay, so now we have the radial corrections. We have the vertical focusing, and that means our muons are stored. So now they're in the storage room. They can circle there before they die out due to muon decay, right? And then we can record it all. What's next? So measuring. Okay, so that was storing the ring. One thing we talked about applying the magnetic field, but if you remember that formula from before, we have to put the B in there, and for a precision measurement, we have to know that B to really great detail. So we need to measure this magnetic field. So I'm not going to go much into detail here. It's another subject, but we measure these things with something called NMR probe. So that's a nuclear magnetic resonance probe. This kind of stuff. Nuclear magnetic resonance. When you go and take an MRI. Now that's works on the same principle. So what I'm just going to say is that we have this probe to measure the magnetic field. Looks like that. So here again, I'm going to ask you a fundamental question. So we have a bunch of these. So where should we place these probes? So this is multiple. So we could either put them inside the storage region, or we could put them outside of the storage region. So which one should we choose, and why? Any guesses? Some guesses? You have 50 chance to be right. Yeah. Okay. Anyone think we should put them on the inside? Okay, that's pretty cool. And what's your okay? Great answer. Great answer. Yeah, you want to have them inside so that you can really get an accurate measurement. So the answer is we put them outside, because what you said. So here's a fundamental thing about particle physics. We have this beam in your storage area, or whenever tube that you're using, your beam is there. You don't want to stuff in front of your beam unnecessarily, okay? Because it's otherwise going to interact with the beam. So these probes are placed outside, okay? I asked the other question, how many should we place? Question? You don't know how many we have. Like, how can you answer this question? I will answer this question myself. We should put all of them, okay? So there, look at that. So those blue things, those are on the upper plane, where the probes lie, and the orange ones are the lower, below the storage region plane. So there are a bunch of them, and you can see like all these data accumulates into mapping the B fields. Okay, so that's what it takes to get this precision measurement. But you too were also right, because we really need to know what the magnetic field inside the storage region, right? Because that's what the muon is experiencing. So we need to do that. So how do we do that? So to do that, how can we measure inside of the storage region? Any ideas? Yeah. Yeah, we could do that. We could do that, but that's not what we want to do. We want to really measure that. We want to go in there, and here's what we came up with. In fact, this was a part of the original experiment as well. We have a trolley. Okay, we have this little train going inside the storage ring, and it measures data. Obviously, you don't do this when like beam is going, right? You do this when you don't have beam. So you turn the magnet on, put the trolley. So this is a trolley. It carries these probes, red dots, and it's a side cross-sectional view here, like they're aligned so. You put the trolley on the rails, and it just starts this journey. Turn the magnet on. It goes around the ring and measures the magnetic field inside the storage region. This is better because you don't want to like constantly be having like multiple ports like entering into the storage region. What I didn't mention you is that like the storage region actually runs at vacuum. There are pumps. There's constantly pumping out like what stuff in there in the storage region, because when we want to run, we don't want other particles interacting with our muons, right? So when you have a vacuum environment, you don't want to like you have too much like source of leaks, a bunch of entry points into your vacuum. So that's why we have that rail, we have that trolley. So the trolley goes around the ring and then creates these beautiful maps, magnetic field maps, like a bunch of them, right? Because it goes slowly, and at each stop, it measures the magnetic field, and then you culminate that into what the muon is actually seeing at the center. Usually, this is like a typical measurement. Like you take a measurement there, you go around, you have another measurement there, kind of interpolate between. But it's a really precise measurement and really shows you what the muon is actually experiencing. So that's what we do. Okay, so here's the fun part. So we need we need detectors. So for this, I actually created some animations. But let's answer some fundamental questions first. Let's remember what we learned about in the first part. So what are we trying to measure? The G factor, yeah. And how are we going to do that? We're measuring, like we're calculating that, but what are we measuring? You're almost correct. The anomaly, yeah, that ties in, yeah, we're doing that, but what are we really measuring? It's like, we put something in there and we get the anomaly. Yeah, so we're measuring the spin precession, right? That's spin precession frequency, which we call omega A. Remember, you put the frequency in there, you put the B field in there, and then you get the anomaly. So, yeah, that's we're trying to find the precision frequency, how that spin rotates. The next question is, how do we detect muon spin precessing? So we need, how do we do that? You already answered that, right? To put detectors, but here's the more like detailed answer. You need to look out for this decay positrons. Okay? So we talked about muon decay. So let's recap. So they go in there into the storage ring, and they start decaying because a muon is not a stable particle. They will decay into this positron. Okay. So this positron then will go, and if you can like put a detector like in front of it, of this positron, we know that we catch that positron and tell, okay, there was a muon there. Okay? So, and this is, and here's the animation. So this is like pretty fundamental. Like this is the base concept of the experiment. So we should be really understanding this one. So here I'll show you. So that's the B field looking toward us. The pink arrows coming at us. Here's the muon, that like pretty exaggerated muon. This is just I didn't put like anything else in there because this makes for like a nicer animation. So the squares, I placed detectors like around the ring. Okay, this is like kind of inside the ring. And the red arrow shows the momentum of the particle. That's the direction it's taking. And the blue one is the spin. So the first I will show you the G equals to 2 case. Okay, because that's our like comparison case. Let's see what happens when we do that. And when G is equal to, remember, the momentum and the spin are locked. So that's why they're like that. Okay. So what happens here is the positrons are emitted. They're decay. So one thing I haven't maybe mentioned is that, for a physical fact, is that the decay product, the positron, is emitted in the same direction as the spin. Okay, this is the outcome of something we call like parity. But it's a super cool concept. But I don't have like time to go into that. You could look that up, parity and parity violation. But due to that, it's the positron that's emitted, that the muon decaying, is going should be going the same direction as the spin, the blue arrow. It's kind of going towards the inside, right? So why is that happening? Yeah, magnetic field. Yeah, remember, that B field. It's kind of complicated, right? The B field is looking at us, but the force it's exerting on the muon, that's radially inward. That's how we got the radial focusing. So what happens is that, like, when that muon is that positron is emitted, it just immediately curves into these detectors. So, like, this placement of detectors seems like okay. But like, if the G was to be 2, all we see is like this flat distribution then, because it's always the same. There is no frequency. It's going around. It's what we call the cyclotron frequency. It's just going around the ring, and then you see some positrons coming out, and it's just a flat distribution. Now, for the next, hopefully that's clear. Makes sense. So now I did the same thing with G not equal to. Okay, so now this G is bigger than 2. So now we're going to see the precession movement. Okay, and that's what all this experiment is built upon, the fundamental idea. When that happens, that spin is going to start rotating, right? How that plays. So this is how it goes. you see that spin is precessing around the momentum direction. And we talked about how the positron emitted mostly along the spin direction. So it creates this nice spiral. So now things are more interesting. They're lighting up. The detectors are lighting up. But here's something to note. So here's the idea. This the $1 million idea. So since it's spin and the positrons emitted in the direction of the spin, whenever that blue arrow is towards the detectors, all these positrons just hit the detector. But whenever it's on the other direction, some of them like miss, as you can see, right? Not all of them gets to the detector. So that means, due to this frequency, this precession frequency, when the spin is directed towards the detectors, you have more events in the detector. When it's facing away from the detector, you get less events. Okay, and that oscillation of events, like going up and down, up and down, up and down, will give you the precession frequency. Yes. The G is not gravity. This is not G. In fact, in this simulation, there is no gravity. I don't put gravity in here. The G is our G factor, the thing that we want to find the anomaly for, right? So we said when G isn't 2 for this spin half particle, it's going to do this precession movement. I know it's confusing, but it has nothing to do with the gravitational constant. This is also known as the gyro ratio. Yeah. Anyway, so that's the G that we're looking for. Okay, hopefully that circles enough times now, and we kind of do this like 10 times. Obviously, we talked about relativistic speeds, right? So it's going at the speed of light. So this is happening much faster. This is kind of all like slowed down considerably, so we can like see positrons emitted and like hit the detector. Okay, so that's the idea. When the spin is in the direction of the detectors, we get more events. When it's in the other direction, we do get less events, and that frequency of that is going to give us the answer we're looking for. Okay, so those detectors are what we call the colorimeters. So colorimeters is usually, they're used everywhere. Usually, they're just some crystals that measures energy. Okay, so this muon comes through here. It decays. That electron curves in and hits the colorimeter. Sorry, the positron, and leaves some energy. So here's how they look. So here's like laser pointed at the crystal, shines bright. It's really nice. So you make an array of them like that, and you have all these like readout equipment like kind of at the back. So when a positron hits like one crystal, you get a signal, and like which crystal you hit. So you have like this special like distribution of hits, and here's it deposits some energy. So here's in this plus like red spot where like the positron hits the colorimeter, and then you say, hey, I have an event there. It just hit me in this crystal, and I record this energy and that positron. So that's basically an event. So with this, actually, we have the fundamentals needed to make the experiment with the detectors. So let's look at that colorimeter data. So here I'm going to show you our G-2 data collected for like for an hour's worth time. Okay, so let's start and see how it goes. It's the plot is divided into different time intervals so that everything can fit in one plot. So you're going to understand what I mean. Okay, so we're running and we're collecting by, so that's what calorimeter is seeing. So when the muon spin is looking the detector's way, see the bump, and when it's looking the other way, it goes down. Then it goes up, then it goes down, okay? So that's the first 100 microseconds, then the 200, 300, and 600. So that's kind of like 10 lifetimes that we talked about. And here, you could see that plot is getting kind of pixelated. That's because there are less muons now, and the beam decohered, and you don't get a nicer plot. If you get more events, you get a better plot. So this is the basic principle of the G-2. Right? Spin looks the detector's way, you see an increase. Spin looks the other way, and you see a decrease. Obviously, you should be asking me, like, how does that 100 microseconds turn into like 1 hour? So when we say 1 hour, it's a collection data from 1 hour. Like you take like multiple runs over an hour, or maybe you take a single run, an hour long, and you just add those, accumulate those events from all the calorimeters, and this is what you get. And that frequency is there. If you can fit that, if you can find that frequency, that's your answer. But is the experiment complete? Well, to some degree, yes. But we're going to say no. So we need a more precise measurement, because that's how scientific advancement is made. We want to do better than our priors. So here's some history. So the first G-2 experiment, sorry, this is a busy slide, but the first experiment was proper experiment done at CERN. The first one is just like using a magnet. What you get is like 4%, like 4,000 of precision. This is like your error that you're making in the measurements. It's pretty rough. The second measurement, they have a storage ring now. Okay, so that we went all through all those steps. So now they can store the muons better. So they, from like 4,000, they go to 270 parts per million. Okay, that's like really small, and we'll get there in a second. What that means, and then they also put electrostatic quadrupole. It's even lower. So then the BNL has most of these things. The experiment that happened 20 years ago. It has the storage ring, electrostatic quadrupoles, kickers, calorimeters, and that gets them 0.5 ppm precision. That's crazy. And again, like without a reference point, you don't know what you're looking at. But I'll give you an example. Anyway, for our purposes, we need to beat BNL and reach 0.1 ppm. That's like what we're trying to do. And this road to precision, it comes with a lot of development on the technical details, but it also comes from the amount of muons, that intensity. You collect more muons for a longer time, then you get a better measurement. So let's try to understand that part per million figure. So, I mean, in the end, what we're looking at is some frequencies, right? So we're trying to differ one frequency from the next. So here's some two sinusoidal waves here that I plotted. At 0.1% level, let's run this. Let's say that they're different only by 0.1%. That's something you could do, like in the frequency domain. Something you can do, you could see easily with your eye, right? So you're looking at it, you're like, okay, here's the anomaly. They're not matching up. There's something there, and then you go and calculate things. So that's how 1.1% looks. So I'm going to do that for 1 per thousand. Okay, again, same picture. Okay, so now I slow it down because there's no difference. So we need to enhance. That detective shows, like the criminal show, the detective comes and enhance the picture. So what we're doing is zooming. Okay, so something you're accustomed to doing on your phone all the time. You zoom, so you get a closer look. So at 10 times zoom, you could barely see that they're the same. Maybe they're somewhat different. okay, 100 times zoom, and you see, like you're zooming in, and you see, like, okay, there's a difference. So now that's something I can measure. So that's 1 part per thousand. We're going to do the same exercise for 1 part per million, which is what we're kind of going for. So with that, obviously, I'm not going to start at 2 times zoom. We're going to delve deeper. So let's try the previous one. 100 times zoom. Now you're zooming in. It's just like still the same picture, from that meme from Office, to like the same picture. 1,000 times zoom. Still, maybe you can barely make it. Okay, so that's like 100,000 times zoom, and you went so much in there, into that like little detail. Now you see, like there's a difference, and that's like kind of like on the 10 ppm level, like for the error, like if you're making this measurement, right? And all of that said, we're still, G-minus is still trying to do 10 times better than all of this. What I showed. So, we need precision. We need to improve on stuff. That's how science and technology advances. So, as a physicist, let's imagine we're physicists. We're all physicists taking on this stuff. We got the magnet from there. We're kind of doing the same experiment, but we're trying to do better. The question we're going to ask ourselves is, how can we do better? Like, what did they got wrong, right? So we have to go back and look at their results. This is a pretty complicated table. We don't need to understand that, but we put our detective hat as physicists and we look at, okay, like there are some errors here. Okay, we look at these numbers, like which ones are big, and we kind of try to address them all. So one of the more egregious ones is this thing called CBO. You look at it, hey, there's this like large number here, and you read through their notes, and they can't really get rid of it or try to understand it. Okay, so we're saying, okay, we're going to make an improvement here. So what is this thing called CBO? So it is spelled out as coherent Betatron oscillation. It basically describes the actual orbit this muon is taking. So this dashed line is the actual, the ideal orbit of the muon. But even if you center the muon in the ring, it's going to wobble. So that's the famous word when you look at in the media, the muon wobbling. Okay, that's due to all these beam dynamics effects. But when you calculate the actual orbit, you see that it's like going all over the place. Of course, everything's exaggerated. And another distinction: the ideal orbit is a closed orbit, meaning it ends where it starts, whereas the actual orbit, it's like these end and the start doesn't line up. That's a key. So like this shows us, how can we understand this? So this, to understand that, we need a better description of the beam that we're seeing, because so far we only had colorimeters, and that it gives us those events going up and down, and that gives us the frequency, but we don't really have any information on what the beam is actually like. So let's give an example here. So here's like a top view of the storage ring. So as the muon like wobbles, it's true, it decays to a positron, and that like if it decays here, it hits here. Sure, if it decays here, like maybe it decayed like far back and it hit here. So there are like a bunch of combinations. The thing that I want to highlight here is like we don't know where that electron is coming from. Like we know that like spin is looking this way, so we see an increase in the event, but we don't really know. So to do that, we put something there in the path of on something called the tracker, a tracking device. So these are like common in like found in almost all like particle physics experiments, and their main goal is to tell you where your particle is going. So we have this thing called the straw tracker. So these are made. So these like aluminum things, like shiny tubes, are made from actual drinking straws. But compared to an actual straw, like you go to McDonald's or something, and you start drinking, these are like much thinner because as the positron goes through, you don't want the positron to interact with a lot of material. You want it as like thin as possible. And inside the straw, there's a wire, a really tiny wire. And when the positron hits one of the straws, it leaves a. Was it a question? Maybe someone not muted. Okay, that's fine. So whenever a positron hits one of these straws, it leaves a signal. Okay. So this will tell us like how the beam looks like. I mean, that's the goal right there. Okay, shown as plot. So let's add the trackers. So we add these trackers here in this direction. So when a positron comes here, it hits these straws. It leaves hits. So when you connect the dots, that's basically what you're doing. You're connecting the dots, and you can reconstruct track back to its origin. So now, like without that matching between the colorimeter data and the tracker, okay, it hit here. It has this, it left a trail like so. I reconstruct that set, and I tell, okay, this one came from here, and this one came from this muon over there. So now, with this tracker, we have a better understanding of what the beam is like. Okay. So, okay, so that's most of the basic and the most important parts of the experiment. So, someone had the brilliant idea of, getting a GoPro camera and put it on the our little trolley. So that's exactly what we did. And then we took like a video inside the ring. So we were actually like, we weren't able to go to the G-2 hall, experimental hall today, but at least, I can show you this. So this is taken over some time. This trolley actually, like, it's not going for speed. Okay, it's not going to get any speed tickets. It's going really slow, and it's also not behaving in a smooth manner. So it's like a jerky movement. So I kind of speed this up, but you see some like jerkiness because it's really hard to like really control that trolley over the whole ring. But let's see. Test out some of the experiments. So we're going in an accelerated speed. Here are the trackers. So when a positron like decays here, it hits the trackers. 1, 2, 3, 4, and then go and then hit the colorimeter. Here are the quads, 4 plates. Okay, this is, there's an electrostatic force forcing the muon like at the center. You can see how jerky the movement is, just like stops, goes, stops, goes, stops, goes, stops. There's a cut there. So more quads. There, remember, 43% of the ring is covered by them. So here's the kickers. So here are those bazookas I mentioned you. Just like gives that super kick. So they look a bit different, only from the sides, and they apply that magnetic field. Here are some quads again, and I think that's the end of the tour. And then there's an exit port that comes here, goes to the side, and the trolley goes down. So that's basically all the stuff we mentioned. I guess we didn't see the colorimeters, but like they're kind of outside the ring. There's this port, and then the positron curves. It just hits the colorimeter. But I showed you a picture of the crystals, so that's good. Okay, finally, with all the technology we have in that ring, we have a profile of the beam. So let's see that. I mean, this is the radial, and this is the vertical, and this is how the beam looks like. This is also animation. -2 data. Let's see that. So yeah, thanks to the trackers, now we know what the beam is doing. This is the actual beam measured by us. You can see it wobbles back and forth radially. The vertical focusing is actually pretty good. This gives you the mean radial position. Basically, the red spot here just shifts, right? So it just goes like so. That's the wobble. And this is the RMS. So the RMS is like this, the wideness of this thing. And it gets, the beam like kind of gets smaller and smaller. First of all, it first decoheres and just the muons decay, and just there's less stuff there. But this is great. So it's an microsecond scale right now, and we see how it's doing. That's maybe the first like lifetime of the thing, and it just keeps going like that. So now we know. Now we know what the beam is doing. That's great. Okay. I looped back over. So let's move on. Discovery. Okay, final part. So obviously there are like more things that we need to do in order to do this measurement, but these are the fundamentals. These are the main principles. Like there are other stuff that we put in and measure and do other than these things, but these are like the fundamentals, the steps and technology that makes this measurement possible. So hopefully you have an idea of what those are and some general understanding of like how to conduct particle physics experiments. So the last step is discovery. That's what like all physicists want to do. Like maybe we want to measure something, but like if it's a discovery, it's a new physics, that's more exciting, more applauded for. So let's go over this formula once more. So G is not equal to 2. So we measured the B field with our NMR probes and our trolley, right? We have this nice picture of how the B is behaving. So we put it there. We measured omega A. So this is same plot that I showed you, but from like one of the runs in run 3. You can see how like with like more events, how nice it is. You usually like when you start a run, you take data for days, months. Okay, so like when you accumulate that data, you have this nice thing, and you fit it with some like extraordinarily complex fitting function. I'm not showing you there, but the idea is that you fit there and you get the frequency of that oscillation, and that's omega A. You put it in here. So you look to your particle physics book to find the E and M in there, and then you get the anomaly. And okay, here is the number, the fractional difference from G equals to 2. So and it comes associated with the error. So I will go over like all the runs we did, just to show you how it evolved over time. So this is the BNL. So like when you put a point in there, like in physicists, your maybe teachers or your professors in the future in college, they're going to be like mad at you, like where's the error bar? Okay, so that's whenever you give a result, you give that error bar. That's parts per million or parts per thousand error that we did. We calculate that and we put it on the dot. There are two things that going into that error calculation. It's usually something we call systematic. That's your error you get from like various parts of your detector, and also the other is statistics, right? Because as you see in a second, more statistics collect, more data you collect, the better your results get. And I'm going to demonstrate that in a second. That's exactly what Fermilab was trying to achieve. So with the run 1, you have this number. You have a better error there. You look at like how these overlap. So they're kind of consistent within that error bars. You go to run 2 and 3. This was the recent run that was analyzed. So you can actually, since they're consistent, you could make the argument, okay, I'm just going to combine these things because they're all the same measurement. And then you end up with run 1 and run 2, 3. That's this thing, and you add the BNL to it as well. That's what we do, and this is the final number with 0.2 ppm. So that's the number. So that's the stuff that we analyzed so far. So we have also run 4, 5, and 6. So we're analyzing that now. I told you essentially the experimental part is over. So once, those are calculated, they will be added here, and, we'll have consistent numbers. So we'll have like something here, like we're kind of confident that it's going to end up here with even like a smaller error bar. That will be our final measurement. So for the discovery, obviously, you go to presses, and you gotta like claim like you find something, but did you really find something? Like maybe you're fooling yourself, or how does it compare to what the theory was suggesting? We talked about standard model at the beginning. So this is the plot we produced to show that. So this is usually it's not a favorite plot right now for muon G- tours, because there is uncertainty about the standard model prediction of this number. So the theories are like working like hard and fast on like resolving this problem. So there's some discrepancy, and they're trying to get their final number. But if they base their latest results from 2020, you get that difference, and we give that difference in what we call sigmas. I will get there, like what that is in a second. Next slide. So 5 sigmas. So that's what physicists like. When you say 5 sigma, you're like, okay, this 5 sigma is the significance of discovery. If it was like 1 sigma, we're like, okay, now this is just a fluke. So I'm going to come to there in a second. Why that is. Here's the experimental value. Here's the standard model value, and then you kind of compare the two. So how do we calculate this thing? So I will give you an example. So another animation that I prepared for this. So what we're going to see here is that I'm going to make predictions, some measurements of the anomaly. I put it on the graph, and we'll see how it evolves over time. So that's our final value. This will be our current value, and this is the standard model value. Let me play this, and it will make sense. So what I'm doing here, I'm adding events. Okay. So that events number is going up by 5. You can see the events here adding to the plot. So the idea is like in the nature, like when you look at distribution of most things, you get what you call a normal distribution, and that usually looks like kind of like bell curve. Okay, maybe you heard these terms before. So this, what you expect, like you keep measuring the same thing, you more or less for that data to fit into like a normal distribution. And this is true for many things, and not true for others. Like maybe if we get age distribution here in the class, it's going to be really biased towards your age because you're all taking the same classes. But like if we look at like a more more larger range, you're going to a distribution of like ages for your high school, for example. You have like 15 years old, 16 years old, 17 years old, whatnot. It's going to curve into this nice normal distribution. So in this picture, however, it's not nice. Okay, so you look at the data, you look at like fit, and it doesn't look like a normal distribution. There's events at 45, and reason for that is we don't have enough statistics. So you put there, you make your fit this bell curve or whatever, or normal distribution. You get the standard deviation. Okay, so calculating the standard deviation there. The standard deviation tell you basically how wide is your distribution. So if you calculate this, how wide your distribution is, and if you ask this question, how far I am from the standard model prediction, basically take this distance, divide by the width of your distribution, and you're saying that our separation is like number. So it currently is 1.6. So a normal distribution with like a 1.6 standard deviation significance that's not good enough to claim discovery, okay? Because I guess I didn't put that here, but when I talk about this distributions and the sigmas, you want to go up to 5 sigmas, and 5 sigmas equals to like 99% of that population in that distribution. That's why that number is important. And here, one key factor again, like you look at this gap here. Our prediction and the standard model is like overlapping, like big time here. Like you see that here where it crosses the standard model. So you don't want to have that. Like you can't claim that you find something. Maybe it's a fluke. Okay, maybe it's just the same number since they're overlapping here. You may ask, like, where is the error for the standard model? I didn't put it there, but it also has its own like this error bar. So you have to also count that in. But what we're trying to say, okay, after 100 events, we have this weird distribution. It almost looks like a normal distribution. You have a mean dashed line, different than our final measurement, so it's pretty off. And you have that overlap, okay? So, and our separation is 1.5 sigma. So at this point, you're saying, okay, not good enough. So either, I'm going to like improve on my detector technology, or I'm going to collect more data, because more data, this width, if it's converging into some number, the standard deviation will get smaller, and you'll have a nicer picture. Okay, so that means you need more statistics, and that's compared to the previous BNL experiment, that's what we're doing. We're collecting more data, thanks to all the muons Fermilab is providing and all the improvements that we're making. We talked about storing more muons. So here is the same thing. I guess this is the final shot, but I'm going to show you the animation again. So of course, at a much faster rate. Otherwise, it'll take forever. So here you go. It's like hundreds of thousands, millions of events adding up. And you can see now we have a much nicer fit. Now it looks like that bell curve that I told you, like the normal distribution. Fit it. It's right on top for the final value we're expecting. And let's that separation getting bigger, and the error is getting smaller as and this is this is not the experiment, right? This is just me simulating the experiment. I'm just adding statistics. So this is the power of the statistics at this. So when we look at the final picture, we have their standard model value here. We are here with this distribution, and then you look at here. Of course, you zoom in maybe, and then there's less of an overlap. In fact, like if you look at like this, there isn't much of a visible overlap. We're far away, and what's that separation power that we talked about? All that much. That's 5 standard deviations for this simulation. So what we have right now is 5.2 with that 2022 calculation. So then you say, okay, we have something. We are sufficiently separated from the model, standard model. We found new physics, right? That's you want to claim. We'll see how things evolve. Yeah. So that's a big thing, and it has effects everywhere. It's making the major. It made the major media outlets. It's put an article from the New York Times. That's the first run article. I mean, this is really important, and let me tell you why that is. Like the last big result from particle experiments was actually Higgs, which was postulated like 60 years ago, right? In 2016, we found Higgs, and there isn't really we weren't able to find any new physics, any sign of new physics since then. Like at CERN, we looked at a lot of different stuff, including supersymmetry and other dimensions, all that, nice theories, but we didn't find any significance. So the G-2 result is really important in that regard. Now it makes the news because it is essentially a new thing that we discover. You're saying, I did this very precise measurement, and it's different, it is different by 5 sigmas from what the theory is predicting. Then the conclusion is there must be new physics. You have to produce new physics to explain the difference. And then, that doesn't, something that standard model can't solve. And now you can actually work on your theories, like crazy theories on why this is happening. And that's why it is fun. You're trying to, as a physicist, you're trying to find new physics. So we're doing the experimental part here. And then when theoretical physicists see this result, they're like, okay, let's get to work and explain this. So this is exactly what they're doing right now. So in the future, when I say future, maybe next year or so, they will update the theoretical physicists who work on this. They will come to a conclusion, update their number. So that means that tension, 5 sigma tension we have, it could decrease or it could stay the same. If it stays the same, that's nice. We have a discovery. What happens if it gets smaller? Then we pack our bags and go home? Or what is the significance of the measurement? So I think at that point, you should tell yourself that you made like an incredible measurement, precise measurement of a fundamental quantity. And even if that's not new physics, now you have like a better understanding of the universe. At least that's what you're left with if you can't make a discovery. But currently we don't know what the answer is. That 5 sigma, it could be real. Maybe it's going to be a fluke, but we'll see. So we're waiting on the standard model to tell us what their latest prediction is. But it is exciting times. It is really a result that particle physics produced that's so major since one of the most major ones since Higgs. Okay. So that's the first one. We actually have the second one. Look at so for the run 2 and 3. This one we just published like a couple of months ago. Look at the headline there. Physicists move one step closer to a theoretical showdown. So most of the outlets were going for that kind of headlines. So yes, obviously we're not fighting with anybody. It's just we're really excited about the results, and we want to make that comparison with the theory and see if we have a discovery in our hand or not. So obviously, I'm being me. I don't really care about New York Times. I only care about what Mark Hamill has to say, and he says, there's evidence of the force has been always with us. So jokes aside, that's really nice. That kind of shows you the effect the news making, among the general audience, and even Luke Skywalker picked on us, which is great. That's really appreciate that. Okay, I think we're at the end of our lecture here. Thanks for attending, and I'm going to leave you with one final meme that I really like for you to think on and ponder. So yeah, thanks.